That's salt. So I said salt. I mean it's sodium. Sodium chloride.
Very good. All right, so oxygen is behaving like which element?
Argon.
No.
Neon.
Neon. So if you look on the periodic table, oxygen's here. It's going to gain 2 electrons. So it behaves like neon. And that's the 2p6 you see right here. Gaining 2 electrons. Any question on that? Alright, so it's going to stop at 2p6 because it's going to lose that electron. So it's behaving like neon. So it loses that. See how it wants to lose an electron?
Well, no, she's not. Wow. That's old. It's the same as my granny. My grandmother, like, just said my grandmother and my girlfriend's parents they're like 50 and 50. And is that you like deal with by these old rules? You can't have a boyfriend.
My dad would kill me about a week. Yeah, you can't date until like 23. And he has money on it.
Alright, so calcium stops on 4s2. That's an element there, Ca. 4s2.
The whole saying is like,
good job.
true love is being able to go with somebody
Yeah, I agree with that.
just like you better have money. You don't have money. It's really not. Women are snobby. Wait, never? Really?
Alright, so what this is going to do, this is going to go to 3p6 because it's going to behave like a noble gas, and the noble gas it behaves like is argon. So argon stops at 3p6. And then nitrogen.
We're best buddies. I don't be honest, I'll be Yeah, you said you did.
Very good. So it's going to behave like which noble gas?
And then we started talking about my parents. We said overall.
The same one up here. Starts at the end. Neon, yeah. So it behaves like neon. So that's what the elements do. They try to behave like the noble gases when they gain and lose electrons. Be like the noble gases. So on page 159, you'll see the table 5.5, which kind of summarizes what Elijah just read. You can see that neon is in the brackets, and that's the configuration. It's the shortcut, so you don't have to write all the 1s2, 2s2, 2p6. It's just a quick way of doing this. Now the following 3s1 tells you what the electron's doing in what shell. It starts with a V. The valence shell. Very good, Cody. Now the valence are the ones that kind of tell you the behavior, whether you're going to gain or lose electrons. Metals want to do what? Raise your hand. What do metals want to do? Do metals want to gain or lose electrons?
Gain.
Metals want to lose, right? So I've mentioned before that men are like metals, right? Men are like metals in that they want to lose electrons, and women are like non-metals and they want to gain. There are other similarities as well. We'll talk more about those later. But just keep in mind that the goal is to get into that noble gas configuration when you gain and lose electrons. So next page, let's read.
3d5 for chromium, and argon 4s1 3d10 for copper. The electron configuration for these two elements, as well as those of several other elements, illustrate the increased stability of half-filled and filled sets of s and d orbitals.
Okay, so I gave you the formula last week for the transition metals, where it was like N, S, 0, N, D, X, if you remember that. So those are the exceptions of the transition metals. And why are there such, I guess you would say, inconsistency with the transition metals? Why is there inconsistency with the transition metals? Right now? Claire? Why is there inconsistency with the transition metals? Okay, well, transition metals means that they can have more than one charge. They're not noble gases. They're not noble. I mean, they don't follow the law of the octaves, in that they have more electrons in their valence shell than 8. So the D can have 10, and the third energy level. So that creates this, I guess you would say, instability. And because of the instability, that creates transition into multiple charges. So when we say transition, we're talking about elements that can have more than one set charge. Like iron can have positive 2 or positive 3. Yeah.
Of which occupy the outermost 3s and 3p orbitals. As shown by sulfur's electron configuration, sulfur has 6 valence electrons. Similarly, although a cesium atom contains 55 electrons, it has just 1 valence electron and 6 s electrons shown in cesium electron.
So in group 1, you're going to see the similar configuration for lithium. Group 2, beryllium. Group 3, boron, and so forth. Remember that on the table that I showed you? So there's a pattern there with the elements. And that's how things are predicted. In life, you want to look for things that you can predict, because that's how you become successful. If you observe patterns and you invest correctly, you can be successful. If you miss a pattern, you'll get upset. Like if you miss investing in Apple, or you missed investing in Microsoft. So we don't know yet the big companies in your generation that you could miss investing in, and be successful. That's just one avenue. You'll have to probably pay more attention to that, because everything seems to be going to 401ks. Like our pension plan is in question right now. That is, they want us now to invest on our own. So that's the direction you're probably going to face. So you need to pay attention to, patterns. Patterns can help you protect yourself. Yes, yes, yes.
For example, the orbital diagram of the unstable carbon atom, which contains 2 electrons in it.
Sublevel associated with each of the atom's orbitals, and includes a superscript representing the number of electrons in the orbital. For example, the electron configuration.
Distributions of electrons related to a sublevel. It is understood that a designation such as nitrogen
of noble gases. Noble gases are the elements in the last column of the periodic table. They have 8 electrons in their outermost orbital, and they are.
Laser is an example of the Balmer series. You can see there on the wall over here a little bit, on the ceiling there, the laser there. So the Balmer series is where electrons are being pushed to the second energy level, and as they're being pushed there, they emit light, right? So I can move this bead, and you'll see that the light kind of changes its dimension there a little bit, right there. Now I had to order this it would be against the law to do what with this? Right, shine it at someone or an airplane. This will shine for 10 miles. You can see there on the board there the light. Yeah. Now this is green, as you can see right there, so it's stronger than the red and the yellow, right? Yeah, it would go 10 miles, this little beam would. Now if I had some smoke, I could actually show you the beam traveling through the air. You could calculate the frequency too. So that is an example of the Balmer series.
Remember she said she's going to the livestock show?
Oh, that's right. Okay, very good. So if you notice up here, Sierra is pointing out to you that when oxygen gains 2 electrons, what's 4 plus 2? 6. And this is going to behave like what noble gas? Starts with an N. No. Little car after it. There's a car named after it. What? The neon. Neon. There's a neon. I think there's a neon car. Is there a neon car? There's not? I thought there was. Maybe there's not. Anyway, so it is a noble gas, neon. It's behaving like. So the elements want to behave like the noble gases because they're stable. They have 6 electrons around it. Now, we're only describing its behavior. We can't tell you why neon is stable with 8. We're just telling you that's what it's doing. So you just have to sometimes accept what nature does. Now, you can complain about it, like when there's an earthquake and there's no warning. You can complain about that. But it's not really going to do you a lot of good. We'd like to have better warning devices associated with earthquakes. We don't do that very well right now. Calcium is Ca. It's going to stop, I believe, on 3s2. Right. Now you can do, it should have, calcium has, it does have 20, so it stops on 4s, you're right. So it's 3p6 4s2. Very good. So right here, if you want to finish this one has 1 electron on the outside. When it loses that, it forms this. Makes sense? And then here, when it loses this, because it's too positive, right, it forms the noble gas underneath of it. This is neon, and what noble gas is this? Do you remember? Starts with A. Argon.
Argon.
So it forms argon. So the noble gases are kind of like, I guess you would say, what everybody wants to be like. Make it stay.
In the 1 orbital, 2 electrons in the 2 orbital, and 1 electron in 2 3.
Noble gas notation uses bracketed symbols. For example, He represents the
Electron dot structure for each group of the law of the octaves. And you can follow it down from lithium to neon. And we can predict what those elements are going to do. Now, when you get into mining, in Kentucky, we mine a lot of coal, right? Well, coal is graded based on what? You might know? High-grade coal compared to low-grade coal? It's graded based on its sulfur content. The high-grade coal has very little sulfur because when you burn it, sulfur goes up into the atmosphere and produces like acid rain. That's a bad thing. Also, when you burn coal, you can release a lot of mercury. I'm not sure which one has more mercury in it, whether the high grade or the low grade does. However, when you are manufacturing the coal for, let's say, burning, you have to deal with the waste. And that's a problem. Where are you going to store it? Now, in Tennessee and other places where there's a lot of coal being mined, you can place the dust in these large ponds. And the problem is sometimes they can break and they can get into your streams, and people don't like that. People don't like having contaminated mercury or metals in their stream or where they're living. See how that could be a problem? Right. So that can get into your well water. Once those heavy metals get into your well water, if you didn't know this, if you go far enough away from Louisville, many people are not on city water. They have to bring in water. They have to have well water brought in. Electrons are pushed to the first energy level. What type of series are you going to observe? Raise your hand. Page 147. The purple arrow. TT? The Lyman. Right, so the last two blocks on this chart, you're going to put Lyman series. Where it says type of radiation, that's going to be the Lyman because it's going to the first. Only electrons going to the first are going to be ultraviolet, the Lyman series. Now if you go to 2 and only 2, what's that going to be? Raise your hand. TT? The Balmer, very good. So we talked earlier in the year that you have to have matter in order to calculate time. So the photon must have mass in order to calculate its speed, because you've got meters per second. You've got a time associated with it. See how there's a second there? So the speed of light has been calculated in a vacuum. We can determine how the speed of light is. It's 3.0 times 10 to the 8 meters per second. I'm sure you've probably heard of the speed of light before. Anybody never heard of the speed of light? You've probably heard of it, but you probably don't know the number associated with it. It's this right here. 3 times 10 to the 8 meters per second. The wavelength can be in a lot of different units, but we're going to call it in meters. So it's just the length of the wave. And then frequency is waves per second. That would be second -1. That's per second. That's associated with this formula right here, speed of light. Now over here we've got energy in joules, Planck's constant, and frequency. Now Planck's constant is a combination of energy and frequency. And you can see that in its units. The units for Planck's constant are energy per wavelength. Now I'm going to show you a little video here in a second that's going to kind of help you understand Planck's constant a little bit better, and then we'll look at the math. So Planck's constant is the minimum energy associated with movement. And what is temperature a measure of? No, temperature is a measure of, it starts with M. Yeah, temperature is a measure of movement. If you remember the initial video, they were showing you the energy coming off of the molecule, and what they were doing, they were changing the temperature. So at a higher temperature, you have more movement. Make sense? There's more energy coming off the molecule. So Planck came up with this. This is the minimum energy that can come off of a molecule. It's Planck's constant. And it's useful for us because it'll allow us to solve for frequency or energy. And you can't do that unless the units cross out. So you have to have accountability. And Planck's constant gives us accountability in the unit. So if we want to solve for, let's say, frequency, we can wave per second, because Planck's constant has that unit in it. You can't just make up numbers without proving it, because then people question your data.
A new line of double-slit lasers. QuantumLaserPointers.com.
So once again, it shows you the
laser shines a coherent beam of light through a film disc containing 2 parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel.
All right, so they're passing that through waves, obviously, which is really interesting that it actually changes the wave direction. It disperses as well. To the Future, there's actually 3 of the movies, Back to the Future 1, 2, and 3. They try to go into the future to see what's going to happen, and then they come back and try to profit or gain from that information, or try to change the past, go to the past and try to, make things different. Now with chemistry, we can predict the future. That's why we have the periodic table. If you know that certain elements are going to behave certain ways, you can say, okay, if I mix these two things, I can predict what's going to happen. That's called chemistry. And if you're paying attention to chemistry, you can then profit from it because you'll know whether something's going to be successful or not. That is, if somebody comes out with a new way to produce a substance and they're telling you this is how they're going to do it, and then they're looking for investors, right? New companies always look for investors. You can say, well, that's probable. That could be a good way to make that new product, or make the product a different way. Now, if you remember with these electron configurations, there's only a 90% probability that's where the electron is going to be found, in these various shapes, right? So a 90% probability is actually pretty good. If you're doing predictions like the future, we are not 90% sure of when an earthquake is going to happen. One just happened the other day in Iraq and Iran. Were you following that?
Yeah, I saw that.
So our predictions on earthquakes, they're probably around 10% or 20%. They can say that there's a window, we believe a window, there's going to be an earthquake. They can do this in California. In the next 5 years, there's maybe an 80% chance there's going to be an earthquake there. They can give you that, but they cannot give you it per day. With the atom, we're pretty good. We can give you a 90% probability the electron is going to be found in that particular shape that you see up here. 90% probability, that's where these electrons are going to be found.
Table 5.4, figure 5.19 illustrates how
Temptation uses bracket symbols. For example, HE.
Moving. At the time, they were using something called Equipartition Theorem to figure out.
So the point is that
A
energy
collection
is
of
going to
particles
be
will release a
emitted
mixture of wavelengths
as you
that's
add
dependent on the
energy.
temperature of the object they make up.
Like a series we were talking
This is
about.
because
As
temperature
you
is a measure of how quickly, on average, all of the particles in an object are moving. At the time, they were using something called Equipartition Theorem to figure out what sort of radiation should be coming out of an object at a given temperature. The idea was that particles wiggle in every way that it's possible to wiggle, and the energy is distributed amongst all of the wiggling variations. These wiggles are also called energy states. This works really well at low temperatures, but as you approach temperatures above a few hundred degrees, the theorem totally stopped working. It gave an answer that was literally infinitely too high. This was because the theorem assumed that there was no minimum energy state, that particles' wiggles could always be a bit smaller. When they went to distribute the energy among all the possible states, too much energy ended up in those infinitely small wiggles. This was obviously far off from what was measured, so they knew that something was wrong, but nobody really knew why. Then, in 1900, Max Planck figured out the solution. In a moment of frustration, he decided to see what would happen if instead of infinite states, there was some minimum, and all of the other energy states were just a multiple of this minimum. And it worked. What went on to be called the Planck law was able to correctly predict the blackbody spectrum even at really high temperatures. And that minimum energy is now called the Planck constant. What Planck...
Okay, so what does that mean? Well, if you look in the book on page 147, they show you that as electrons are pushed, that is, the atom is going to be moving around, it's going to be wiggling, right? Like he was talking about there. There's basically a minimum energy that's going to be given off. So the ultraviolet is the maximum that's shown in the book, right? It's purple. Well, the minimum energy that can be given off is called Planck's constant. There's a mathematical number associated with that. We're going to show you that up here. Oh, the Planck? I know the Planck is. Negative 34 is a very small number. Super small. So this is the smallest energy that's going to come off of a substance. That's Planck's constant. I'll tell you if you're right.
You're right. No, I just did this. It's so write down 1s. I mean 1s1. 1s2. 2s2.
Your sheet, it says 2 negative right here, correction -2, and then right here it says 1 negative. So just be consistent how you write it, whether you put the negative behind the number or in front of it. Both are accepted.
more about noble gases in chapter 6. The noble gas notation uses bracketed symbols. For example, AT represents the electron configuration.
Imposter would be incorrect. The correct configuration are involved in forming chemical bonds. Chemists often represent them visually using a simple shorthand method.
Yeah, things are faster than the speed of light. Particles that are smaller than light travel faster. And we've learned at the beginning of the year, once again, that matter is associated with time. So you can't get a time unless the thing has matter or mass. So light must have mass because you're calculating a second, meters per second, associated with its speed.
So how do we find the mass?
How do you find the mass? It's been mathematically calculated. It has not been experimentally calculated. You can go online and find the formula for that. It also, once again, based on Newton's second law, it says an object will remain at rest unless acted on by an outside force, and force equals mass times acceleration. So the electron is moved by the light when you see these solar calculators. Now it requires certain frequencies. The red is not strong enough to move it, but when you have like a yellow or a green, you've got enough of them together, working together to make a mass strong enough to move it. So this shows you how light the actual photon is. The photon by itself is not strong enough to move an electron.
Are wiggling around. As they wiggle, they emit radiation in the form of electromagnetic waves. Faster wiggles release shorter wavelengths, and slower wiggles release longer wavelengths. A collection of particles will release a mixture of wavelengths that's dependent on the temperature of the object they make up. This is because temperature is a measure of how quickly, on average, all of the particles in an object are moving. At the time they...
So the point of movement. So if I add heat to a substance, just like the Balmer and the Lyman series, you get an outcome as you're pushing the electron in. Things are going to come out, either light, infrared, or ultraviolet. So that's what's happening here. As you are adding energy, things are going to come out. So the Planck's constant is trying to figure out what's the minimum amount of energy that's going to come out. What's the minimum going to come out of the atom? That's the goal of Planck's constant.